Klembt from the University of Würzburg. Sebastian, he did his PhD in 2-6 microcavities under the supervision of Professor Hommel, both in the strong and weak coupling regime. And from what I have been following his work throughout the years, and he has really remained in this area, expanding beyond, of course, weak coupling to strong coupling with a focus on topological effects and quantum simulations in optical lattices. So today, Sebastian actually, after his PhD, he joined, he moved to Würzburg after a short stint at Grenoble, where he became a group leader in 2015, and since 2020, he is a junior professor there, leading a team on the work that we are going to see, hopefully today. So, Sebastian, without any further ado, the floor is yours.
Pavlos, thank you very much for the very kind introduction, and hello to everyone. I should say I hope that you can see me. I cannot see you, which is probably due to my lack of skill in this Teams application. But I'm hopeful that you can see me, and I'm looking very much forward talking to you. I know that this is a polaritonic series, and certainly a part of my talk will actually cover polaritonics and effects that require actually strong light matter coupling, and another part will show you that we can do exciting stuff with vertical cavities even in the weak coupling regime. So my talk is called Topological Photonics and Topological Lasers with Coupled Vertical Resonators. So since I was under the assumption that most people here will be fairly sure what a polariton is, I will give maybe some important clues later on. I wanted to start at a different point, namely at topological physics. And the very beginnings of topological physics actually bring us to the 1980s, where people had available very, very high quality two-dimensional electron gases. So suddenly there was a chance that the mean free path was such that they could actually see quantum effects in the propagation. And a very famous example that all of you, of course, know is the quantum Hall effect that Klaus von Klitzing discovered in 1980 and got the Nobel Prize for in 1985. So you apply a magnetic field, and what it does is, in a way, it does break symmetry. It sets your electrons on an orbit, which makes the bulk of this material insulating. But you have this hopping orbitals at the edge, and in the Landau-Büttiker picture, you can describe this very, very nicely, of course, and you get propagation at the edge. At the time, it was not described in a topological manner, and certainly it was not described as a topological insulator because it required a strong magnetic field. But the idea was actually there that you could have something that is insulating in the bulk, but at the edge has an edge mode that can actually propagate. And then it was the quantum spin Hall effect that was really, and the theoretical work by Bernewijk and Susheng Zhang and others, who really led the way towards topological physics in solid state. Before, topology was really considered a mathematical part of the mathematical field of research, dealing with certain properties of objects that are invariant, and suddenly you could bring those to solid state environment. And what you generally have is you have an interface with a difference in topological invariant, and I will maybe come to that a little bit later. So basically what you do is you have a conventional insulator and you bring that in contact with, in case of the quantum spin Hall effect, with a quantum spin Hall insulator. This is actually done by an inversion of band structures in mercury telluride, for example. But what you get essentially, and this is the crucial point that I want to highlight, is you get again a material that is an insulator in the bulk material, but at the edge you have propagating modes. And in this case, you have modes propagating one way with spin up, and spin down propagates in the other direction, because they see something like an effective magnetic field in the structures. And so what you have in the structures generally is you have edge conductance only. The states are protected against backscattering and scattering into the bulk. The scattering into the bulk is relatively easy as long as the width of your mode right, is smaller, the line width is smaller than the band gap you have in your insulator, there's simply energy-wise no states to scatter to in the bulk. So your mode is actually forced to stay at the edge. And similarly, there's no way of backscattering because simply there are no states to occupy. So Fermi's golden rule tells you cannot go back, you cannot go into the bulk. You have chiral edge states that have to continue propagate at the edge of these samples. And this is coined in the term of robustness, meaning that your excitation is robust against certain perturbation as long as your perturbations are smaller or max compatible to your scalable energies in the system. And this was quite exciting from a fundamental point of view. It's quite important for metrology. So the way we can measure things quite exactly, because in the von Klitzing constant, for example, you have two natural constants at one that you can measure anywhere in the world. So it's also quite useful, or starts to become quite useful, but also it was very interesting in terms of fundamental concepts. So this is where I just started: transport physics, quantum spin Hall effect, and the first topological insulators. And soon after, and in polaritonics community, a lot of you know, of course, our strong ties with concept from cold atoms, people came up with the idea of creating topologically non-trivial band structures in optical lattices. And now these are optical lattices that are defined by lasers and where cold atoms are trapped. And here's some examples. And generally, it's relatively hard to show these effects in let's say in real time. And that's why here I have an example for you on the right, and I hope it works. When I click this, then it should start. So here we can see a topological edge mode in real time. Each one of them is a pendulum, and they are connected in a way such that an Hamiltonian is realized that actually is topologically non-trivial. And you can see that the amplitude goes around, the strongest amplitude is around the edge here. It's not completely perfectly insulating, but it's, I think, a very neat example by Sebastian Huber and colleagues from ETH Zurich, where they showed that actually you can create a topologically non-trivial Hamiltonian in pretty much any system where you have some physical object that you can couple to another one. In this case, it's very macroscopic. So each pendulum, I think, weighs something of the order of 500 grams. So so obviously it didn't take long till people realized that this is something very interesting to be brought into photonics, because photonics were interesting for our everyday life. Actually, the reason I can talk to you so smoothly is because the laser and the fiber behind me is connecting us via the internet. So photonics is naturally at the border of fundamental physics and optics and application as well. So it was Duncan Haldane, one of the three people who received the Nobel Prize for, let's just say, topological physics in 2016, who came up with the idea that you can break time reversal symmetry in order to make directional optical waveguides. So this was the idea, to say, listen, we know mathematically how you can create edge states in a system. Then there's not really a reason why you cannot do it in photonics. However, doing it with a magnetic field is fairly difficult, because photons don't really react to that. You would need strange material and absurd magnetic fields. So basically, you have to think hard about what kind of systems you can create, and people have done that. So the first, let's say, topological insulator with electromagnetic waves was in the microwave regime by Marian Soljacic, who had this rather large array of reflectors in a plane. And then, of course, the first photonic topological insulators in Floquet waveguides, silicon photonics, by groups of Muti Segev and Mohamed Hafezi and colleagues, and later therefore followed metamaterials by Alex Kanikayev and others. And then, of course, this is a slide that I use relatively regularly. It was actually our group who found a way to create topological insulators using exciton-polaritons. And here actually, and I will come to that in a bit more detail later, magnetic field is quite crucial, but not in the way that you would naively think coming from the quantum Hall effect. So let's take one really simple step into polaritonics. I'm fairly sure every one of you knows this. This is what we very typically working with. So there's a semiconductor microcavity with a lower dBr and upper dBr with a bit less mirror pairs, so we can extract light to the bottom. There's some active region that very typically for most things you will see today is gallium arsenide or indium gallium arsenide quantum wells in gallium arsenide, aluminum gallium arsenide. So that's a fairly standard system. And then here you already saw the lower polariton, the upper polariton, and the characteristic anti-crossing of the new eigenmodes that are, of course, your upper and lower polariton here in a white light reflectivity measurement. And that's quite interesting because, of course, all of you know what you can do with strong light matter coupling and the effect that now you have strongly interacting lights. So I'm not about to give you a full introduction into everything there is to know about polaritonics, but confinement. Confinement is actually fairly easy. And quite early on, people managed to create individual pillars. And you see that, of course, in K-space that you can measure directly, you see localized modes, and then you can create a molecule. So actually you can use tight binding to describe this. If you have some overlap between two micropillars, you see that the S band suddenly has a binding and anti-binding band, the P band, the D band, and so on and so forth. And if you extend that, you can actually create band structures. Here I have an example of the honeycomb lattice. Of course, now you have to be quite careful that you create, that you describe the directions properly, because it is now important how you actually place your sample in the cryostat and how it is in comparison to the slit of your spectrometer. So you have to make sure that you know actually in which direction in the Brion zone you're measuring. But this is a fairly straightforward way, and there's some overview because I cannot give this talk without acknowledging some work that has been done in the community. I have to say I focused here on two-dimensional polariton lattices, and mostly because the very first paper by the Yamamoto group from 2007 actually isn't really two-dimensional. It's metallic stripes that were able to shape the potential landscape and create minima and maxima for the polaritons to reside in, and is one of the first papers who showed this idea that you can actually trap a polariton condensate and make it interact with another one. And then, of course, there is a plethora of methods that you can use. There's surface acoustic waves, like here by Salder-Mendes and colleagues measured in 2013. And then, of course, very prominently, and I took one of these very pretty, very early papers from the group of Jacqueline Bloch, where they etch down micropillars and have this beautiful honeycomb lattice, which is a technique that you will also see later on. Something that has been developed to some extent, and it started in Lausanne, but then brought to two-dimensional lattices here in Würzburg, is actually this etch and overgrowth design where you create a shallow etched potential and then you overgrow it. So what you essentially have is not a semiconductor air interface, but rather a locally elongated cavity, which then is redshifted with comparison to the surrounding material and thus traps polaritons. And of course, we all know that polaritons are interacting, so you can locally blue shift them. And here you see some examples by Hamid Ohadi, and here by our host, Pavlos Lakodakis and co-workers, where you can create intricate lattices that emulate Ising Hamiltonians by creating localized sites due to local blue shift around that by using amazing spatial light modulator technology. You find, of course, here work for the group of from Sheffield, emulating Dresselhaus effect behavior and honeycomb lattices. And relatively recently starting, also you see new materials adding to that. So all of this is gallium arsenide, if I'm not mistaken, in any shape or form. And here you see that people are successfully trying to bring two-dimensional polariton lattice actually to organic materials here in the group of Thilo-Stöffel. So there was quite some fundamental work to start with, and yes, I should mention that this is of course not complete. If I forgot your paper, I'm very sorry. This was really meant to give a first overview about confinement techniques and polaritonic lattices. So when it comes to topology, let's take one step back, and maybe we will come to two dimensions a bit later. Let's start with the most simple one, and this is actually the SSH model. I consider it the Drosophila of topological physics. So really, the one of the simplest model that you can come up with. It comes actually from carbon bonds in chain molecules, acetylene, I think in this case. And what it is you have a staggering of a strong bond, a weak bond, a strong, a weak, a strong, a weak, a strong, a weak. And when you describe this in tight binding, actually you can see that there are two different ways to create this chain. One of them starting with a strong bond, and one of them starting with a weak bond. And they're actually different. And what you can show quite straightforwardly is you can call this two couplings V and W. You can of course call them what you like, and then you can have a look what happens with the band structure and with what happens when you go around and integrate around a point in K-space. And there we find that for one way of ordering the chain with a weak defect at the end, you get, of course, a gap due to the fact that your unit cell is now contains now two pillars. If everything is the same, there is no gap, of course. But here, when you go around the singularity, you actually acquire a phase, and that's called a Zach phase. That's similar to a Chern number, and now you suddenly end up with a topological defect. Sorry, and you can create this defect in two ways. It's actually the weakly coupled pillar, either at the edge or at an interface defect, and I will show you exactly what I mean by that. And this was done first, I should mention that, in this dimerized coupling model by the group of Jacqueline Bloch. So they were the very first to show that this can be done. Because how do you create actually a strong and weak bond when the only thing you have available is actually the distance here? Well, very easy. You could try to change the distances. I can tell you that also this works, but you can find a smarter way of doing that by not looking at the S mode, but by looking at the P mode. And this is what they did first. And then we showed that it can also be done in this edge and overgrowth structure that we believe has maybe some advantages. What you have is you have a PX and a PY mode, and they have different shapes and thus different overlap. And this would be, for example, this would be a strong overlap in this direction. This would be a weak overlap. And what it does is for one of your modes, it actually creates a weak defect at the edge. Now it's quite important. This is not localized because it's decoupled from the rest. You can pump all of it and you have a bulk, if you want, band structure, but still you have an exponentially localized, topologically protected defect here. So here you see the S mode. This is a measurement in this edge and overgrowth structure that we made, where we can control the coupling very, very accurately. And here you see the localized defect. And what you can do then, of course, is you can show that this defect is actually showing laser emission. So you have nonlinear light output, you have a decrease in the line width quite suddenly at the threshold, and you have a blue shift throughout that you can compare with your polariton density and from models quite neatly. And you can show how much bulk is actually needed in order to support this topological edge states. And we could actually see, well, clearly see the topological defect with a total number of pillars of only 5. So relatively little bulk, if you want, and then 2 defects here. All right. And then you can go a step further and show which at the beginning of polaritonics, because you have no inversion, again, we have weak and strong coupling, and the whole concepts of lasing actually stem from population inversion, the idea of Albert Einstein from 1916. And here you don't have that. This is a polaritonic system. You don't have that, but you can show quite neatly also in this localized topological edge defects that when you do an HBT measurement and you measure second order coherence at tau equals 0, you can see that you go from a thermal state to a very, very good 1.07. We actually now have had some values that were below that, very close to 1, so very pure lasing state from these topological defects. All right, this was quite nice. And I should also say that when you deal with lattices, or when you're considering going into lattices, it's quite important that also theoretically you understand what you do. And most of you will be familiar with Gross-Mitajewski model that originally has been used for weakly interacting cold atoms. And of course, you can apply it to exciton-polaritons, but you can do so also very successfully with potential landscapes like you get in lattices. So there, we're working closely together with Oleg Egorov from Jena and, of course, Timothy Liu from Singapore. So essentially what you do is you describe density and velocity, and you have the interaction that you get because you're dealing with part exciton quasi-particles. You have to put decay and pump because you have a driven dissipative system and not cold atoms. And you have to introduce this potential, which essentially you have to adapt to your experiment. And if you do so, you can actually do numerical experiments that quite accurately reproduce your findings without having a plethora of independent degrees of freedom that you can adjust. So you can really compare this to your experiments, actually taking into account, and that's meant by modified, really taking into account the detuning and thus the interaction here. So I thought that's something worth mentioning. And maybe one last thing for SSH before we come to something even more exciting is a technological step for us. So we took one of those interface defects. In this case, it's a zigzag chain here, and here you have a domain boundary defect between one zigzag chain and the other one. And this is a measurement here, so you see again this localized defects. And finally, of course, at the very end, we want to go to electrical injection. So we're not there yet because it's quite difficult to really get your current path through the defect right to get deterministically lasing from a topological defect. However, what we found is something we were equally interested about, and that is electro-optical switching. Because one thing that you can do when you apply a voltage is you can make use of the quantum confined Stark effect. Because normally when we think about changing the detuning, and thus the stage in which we most likely have polariton condensation, we would change the photonic part. We would change the radial detuning of a wafer. So the exciton we would consider more or less fixed, and we would change the photonic component by changing the length of the microcavity. And this typically looks like that. So here you see your SSH mode for a variation of detunings on the wafer, going from roughly minus 1.8 Rabi splittings to around 4 Rabi splittings here. And what we found is that you can actually do this in two ways. Of course, you can do it by a relative radial wafer position. So you go towards the center or the edge and you shift towards the blue or towards the red in terms of detuning. But as well, you can do this in applying a reverse bias here, thus shifting the exciton by actually quite some amount, and thus having relatively accurate control over your detuning in the system. And thus you can use non-resonant excitation, and you can actually see when you look at the intensities of the individual bands. So you have some higher bands, you have an anti-binding P band, and then you have the topological state. You can choose your reverse bias such that you're dominated by this this gap state, this topological defect that you can see here, and thus have lasing from this state and switch this basically on and off, and choosing to condense in the trivial bulk. So essentially here in the bulk of this SSH chains, or at the topological defect. And of course, we have electrical pumping in the end in mind, and we're actually on a very good way there. I have a very good student working on that, courageously facing all the technological difficulties that come with that. One thing that we think is typically so naturally that we do not even think about mentioning it is the fact that when you have a polariton, it has, among many other things, the great advantage that you can actually see it move. And of course, you do not see a single polariton move, but you have an inherently dissipative system that will always lose some photons. And that's the way we know how our polaritons propagate, at which energy they are, and so on and so forth. So here you see a waveguide array that my student Johannes actually created, and we published that. It's on Bloch oscillations. I won't go too much into that, but what you see, of course, is you excite your polaritons here, they start propagating. You see this Bloch oscillations, they are the result of an energy gradient that we engineered here. But what you see is you see a polariton wave package propagating while it's doing it, which of course you do not have when you talk to your colleagues who work with ring resonators or who work with fibers or anything. They can say it went in here, it came out there, but what happened in between is really nothing I can access. So this is something that we can actually use in the exciton-polariton system, that your light predominantly oscillates between two mirrors, but also propagates in the plane. All right. And that's, of course, the idea coming to the 2D topological insulators. It started, of course, with graphene, where Kane and Mealy came up with the idea that if you have sufficient spin-orbit interaction, you can actually see a topological edge mode here. And then spin-orbit interaction, carbon is a very light atom. People are now trying bismuth and other things to create hexagonal monolayers like that, but it has a very weak spin-orbit interaction. So it is relatively straightforward to say, well, our idea is let's go to some artificial system where we have tuning knobs that allow us to artificially create something that looks like spin-orbit interaction. And this is, of course, what I'm going to talk about now. So you use the tight binding model, you have this band structures, this features this Dirac cones, and you can describe them very neatly by nearest neighbor and next nearest neighbor interaction. And then you get the band structures that all of you know. You have this Dirac cone dispersion at the K point. You see the 6 K points here, and you see how nice it is that you can see real space and K space when you do a tomography. So you shift one of your lenses in front of your spectrometer, you have access to either full K space and energy or real space and energy. And this is what we're doing here. So now you see that generally our band structure is very good agreement. At the zeroth Brion zone, you have destructive interference in the far field. Thus, you do not see the anti-binding band here. If you go to the second Brion zone, you actually do that. So whenever you see that, it's also very nicely presented in the paper by Jacques Mel that I showed you earlier, that this is the case. You get this nice Dirac cone dispersion. All right, and then you do two things. You combine actually a way to break symmetry and a way to create something that looks like spin-orbit interaction. And if you're interested in that in a bit more detail, how this is done, you can read these theoretical papers by the group of Tim Liu and Anton Nalitov that basically appeared back to back. And before people showed that you can actually use TETM splitting to create something that really looks exactly like spin-orbit interaction. So you get this, you don't get a band gap yet, but you go from 2 bands to this situation here. And then if you break symmetry via Zeeman splitting, so the magnetic field here does nothing else but basically shift your 2 pseudospin components, your sigma plus and sigma minus in energy. When you combine the 2 of them, what you get is actually you get a topological gap. And because here your unit cell contains 2 singularities, a k point and a k prime point, if you integrate around that, you accumulate, go to a Chern number of 2, which means you have 2 propagating modes in one direction, and the blue ones would actually, if you think so, on the other side of the sample would be the ones that go in the opposite direction. And that's what we measured. So you measure the band structure, you see that predominantly you are in some trivial mode, that it's a large laser spot on your lattice in real space. Here you see the edge of the sample, and you see a little bit of intensity here already in the gap. And if you do a tomography and focus on that, you see that this is at the edge in the topological gap. And you see that this mode goes around the edge and around a defect here. Going around a defect is actually quite good, but going around this edge was really the crucial part, because what you have is you have a zigzag chain and you have an armchair. And while there is a trivial TAM mode in a zigzag chain, there's nothing like this, and we know this from graphene quite exactly in an armchair. And the reason you really have a mode is that the polaritons can only propagate along the edge of the sample. They cannot scatter back, and that's why they have to go also in the armchair mode, where there's no trivial reason to go there. So that's very nice. The magnetic field wouldn't do anything if there wouldn't be, or would do very, very little, if there wouldn't be an excitonic component, and thus a Zeeman splitting that you can use. But of course, this is not terribly convenient in terms of parameter space. That's very cold, and that's very large magnetic field. So we thought of something else. And the community was already there in topological physics. People were talking about actually coupling non-linearities. And that is the birth of what is now called topological lasers. And I should make some distinction, because this topological lasers, I showed you before, lasing from a topological defect. And you can call this a topological laser without any problem. It's just important that you explain what you mean exactly. And in this context of topological lasers in a broader sense, what is meant is that you have a two-dimensional lattice with a one-dimensional interface, in which your laser cavity is actually a coupled set of lasers along this interface. So it's not a single defect that is zero-dimensional, but it is a one-dimensional defect here in the case of this gyrotropic material, gadolinium gallium garnet. It has a very small intrinsic magnetic field, a couple of Ørsted. So it creates a very small gap that is much smaller than the line width of this lasers. Nevertheless, the group of Boubacar-Kanté saw some lasing around this arbitrarily defined edge. And then there was the group of Moti Segev, who used a model by Mohamed Hafezi. So these connectors actually create a synthetic gauge field that looks like a magnetic field, and they couple these ring resonators. Every one of them is a laser. Everything is in plane, so the laser are coupled around this edge, and they could actually show that the topological model was more efficient than the trivial one, and had some other. So not everything was already set here, but they could show that the topological laser has several advantages. It has an improved input-output characteristic, and they managed, because when you stay within the topological gap, they managed that there's a very good distribution in terms of the wavelength where this interface would emit. So in the trivial case, you had a slight deviation from point to point in the wavelength where your lasing activity was, where it was much more homogeneous in the topological case. And I will come to that later. So we already know how it works with our microcavities. So things are different. We have the oscillation in Z direction, and then of course the coupling takes place in the XY plane. And I should stress that now we are leaving polaritonics for a bit, and we will see that what we implemented here actually can work in the weak coupling regime. It's a purely photonic effect that we implemented. So instead of a quantum well, or several ones that we would normally have, we have quantum dots, and we have quite a lot of them. So there's no individual quantum dots single photon physics, but you have a large amount of quantum dots that have been known that they are very well suited for active material and lasers. And this vertical cavity surface emitting lasers, which are very close to our polariton cavities, of course, have quite some advantages. They're very compact. My computer mouse is using one of those. If you have an iPhone, it has a infrared LiDAR laser that uses the similar design. They are small, they're very industry friendly, they can be modulated very fast, which is quite interesting. And if you look at the Yole development report, you see that there's also a lot of money in there, which is not the reason we are in it. But I can tell you that generally when you do something new in the field of lasers, there are people who are going to call you and are very interested what you're going to do with this next. So this is lasers are always quite interesting and quite fun to play with. And now the problem. You have very small lasers and they are typically limited by their output power. And you cannot make a single one larger. At some point, the concept will break down. So what people obviously thought of doing is create an array of individual lasers, right? Mode lock them in order they emit at the same wavelength and with the same phase. Because if you don't do it in the same phase, which what we have in our basement for our laser pumps, it's basically a very, very bright flashlight. So more or less incoherent light that is more or less at the same wavelength, but it loses this coherent laser properties. And the problem in the 90s, when people tried this actually to quite some extent, here a beautiful visualization that was done by Alex Dikopoltsev from Technion, from the group of Motisegev, was it didn't work. And here is how he attempted of describing what you actually see. So you create a array of perfectly ordered lasers, right? And if they are perfectly ordered, you can in principle see one super mode that is at one wavelength and that is coherent. But the reality is you're dealing with semiconductors. There is quite some disorder in the system. It's of course, this is exaggerated. Sorry, I have some bug here. This is quite exaggerated, but this is the reality we're facing. And what it means is that different parts have slightly different wavelengths. It's not as bad as that, but a slightly different wavelength, and they lace with a different phase. So you have separated parts that act as one group here, one group there, one group there. And then people kind of stopped trying. I will not say that there are zero papers, but the majority of what we found for phase locking and injection locking between multiple lasers is from the late 80s to the mid 90s. So this is still quite an open problem. So when the size grows, it becomes increasingly unlikely that you will actually lock these lasers. And here we thought, well, there is topology. In topological insulator, you have a mode that has non-zero group velocity. So it has to propagate. It cannot localize in one patch or the other patch. So you have a suppression of localized mode because what has to propagate cannot localize. And you have a system that is robust to some extent against disorder and defects. So that's quite exciting. So essentially what we do is we combine micro lasers with concepts of topology to create topological lasers with vertical resonators. And I will come to the details of this interface. I hope it only lacks on my screen. My cursor is quite slow at the moment. So again, we do the same thing. Now it's a VCSEL array. We take one little piece of it, we take two, we take several, we get a band structure. Now, first of all, we are in weak coupling now, so applying a strong magnetic field wouldn't break time reversal symmetry here, so we had to think of a different model. And what we used is the model by Wu and Hu that's called the topological crystalline insulator model. That's called crystalline not because we do it with a semiconductor crystal, but you create a crystalline pattern of coupled resonators, and the topology lies within that. So what you essentially do is you take a honeycomb lattice and you look at one of these benzene rings and you contract one of those and you expand one of those. So at the end, you're left with something that's not a honeycomb lattice anymore, but you have a much larger unit cell now that is of the order of this benzene ring. So you have to accurately get all these couplings right, which are done by changing the distances of these individual resonators, 2 couplings here, a weak and a strong one, 2 here, and then you create an interface. And what Wu and Hu have showed in this paper is that when you consider photonic modes, you can actually look which kind of parts of the dispersion are actually have which characteristic in terms of P and D modes. And what they found is that this actually inverts at the interface. So that whether this is P type or D type, if you're interested in that in detail, I have to refer you to this paper. What you get is you get an interface mode right here, and here you get a double closed Dirac cone dispersion, so a topological interface defect. That is a one-dimensional channel in a two-dimensional system. And this does not require any magnetic field as such. And this is what we did. You will see that there's actually some disorder, because when you etch this with plasma etching, you will see that these holes are not perfectly hexagonal and they are not perfectly homogeneous. However, we could show that we could manage to balance really these 5 couplings, because normally in a honeycomb lattice you have 1, now you have 2 plus 1 at the interface, and you have to accurately balance them such that the gaps have a similar size and you get this interface mode between the compressed and the stretched one. And this is what we did. Here I included this hexagon for convenience, because otherwise it's rather hard to see where the interface is. So this is white light, and we chose to create a closed interface in the form of a hexagon here that in this case has exactly 30 sides. And then we measured the compressed one. There's a gap, which is what we expected. There is the stretched one, so there's a topological gap, and then there's the interface, and at the interface you actually see a mode just as expected. So absolute numbers are not that important, but we have band gaps here of the order of half a milli-electron volt. And this is important because we will have to compare this to the line width of our lasing system in order to see whether we would expect our system to be topologically protected. And this is what we did next. So there's below threshold, this is measured at 4K. We see this interface that is pumped by a spatial light modulator, and above you see the lasing coming from this interface. A strong non-linearity in the input-output, a decrease in line width, anything that you would expect. You have a linear spectrum that shows you a relatively broad mode spectrum, and here in the gap you actually see lasing. The blue curve is measured on a single site, pinhole closed. You measure a single site, so you get the line width here, and it's a bit narrow, but for the overall full laser system of 30 coupled VCSELs at the interface, you get a line width of roughly 250 micro EV, which is half of your topological gap. So in terms of topological photonics, that's not too bad to have a line that is a factor of 2 smaller than your topological gap. So we could look at its properties, and the most important properties is the question, are those lasers coherent with each other? So what we decided to do is look for G1 spatial coherence here and use a Michelson interferometer, which was already done in Jacek Kasprzyak's famous paper that showed the first Bose-Einstein condensation in polaritons. And here we didn't invert in 2 directions, but we did it mirror symmetrically, so along these lines using a prism. So these are 2 autocorrelation points here, and all the other points are superimposed on the opposite side. And what we see is we see the fringing here, and what we now do is we look for the fringe intensity. You can do this neatly by a 2D Fourier transform, look for the coherent part, throw away the rest, and you get your coherence function, which is what is plotted here. And you can see that this is really fully coherent throughout this array. You, of course, have quite a bit of noise because you do not have lasers everywhere, and there is, well, you look at fringes, and fringes can only be where there is intensity. So when there is a little gap in here, there's no intensity, of course, so there cannot be correlation, but you see that there's neatly a high level of spatial coherence around this interface. And then you can compare this with a trivial case where you have only coherence at the autocorrelation point, so where you superimpose a laser with itself. And here it radically drops when you pump it with this hexagonal spot. So this is what you can see here. Whereas when you go around this, you see that is scattered around 1, a bit below 1 actually. So here you have the topological array and the trivial array. You have several modes that actually are switching on, which is another reason why you cannot even expect to have a large spatial correlation here. All right, so this is published in this paper here in Science last year. Yes, maybe exactly. So we compared this with theoretical modeling, and we could actually see that this fits quite well. So typically, what you have in the trivial one is you lace from this mode in the P band, which is the most likely to start lasing and recoupling here, and you see that, and you have some other contributions. Whereas in the topological case, really your lasing stems from this this 2 modes here, where you have the maximum overlap with the pump, and these experiments fit very neatly the measurements that we have done. All right, so you have lasing with zero group velocity in the case of the trivial one. Different emitters have slightly different properties, and the result, you have individual groups in the trivial case. So you have the opposite of what you have in the topological sense. And now something else that we found quite interesting is we only use the quantum dots as emitter material, and it's a relatively broad ensemble. So we were thinking, what if we do not just use a different device, but the very same device and heat it up? And we could heat it up to 200 Kelvin, and we still would have gain overlap between the quantum dots and the photonic modes. And we could see, well, there is a bit more noise on the system, but we could see that the system remains quite robust and quite coherent along this interface. You still have a quite narrow line shape. This actually doesn't change at all. The distribution is a bit more spread, but you still see that this topological lasing effect survives when you heat the exact same sample from 4 Kelvin to 200 Kelvin. We couldn't go to room temperature here, which would have been a good selling point if you want, but there our quantum dots were completely dark, so we wouldn't have any gain material. All right. So the important point here is actually in the vertical cavity, because when you couple ring lasers, as interesting as this is, and there's fascinating works being done on it, you have one issue, and that is that the propagation of light and the direction of topological propagation are in the same plane. So you have to find a way to outcouple your light through an outcoupler, and then if you have very high intensities, it will eventually break down, and you have to find a way to get out of plane by some couplers, so that's not so easy. So here in this vertical system, you have a different situation. You have the majority of your light field oscillating in Z direction between your mirrors, but you have some propagation in the system, and how this exactly works, we currently work on with street camera techniques together with a group of Manfred Bayer, and of course still in collaboration with Muti Segev's group, whom we have done all this work. So to find out the role of this propagation in plane and the coupling between individual resonators, and then the outcoupling through the surface of the sample, which makes it very easy to collect the light as opposed to this ring resonator system. All right, so that's the conclusion. We were very happy that we were picked by Physics World as a top 10 breakthrough. We were in the top 10 list. We didn't win the thing. I think this was something with optomechanic couplings, which also quite fascinating project. And this was a collaboration between 2 groups, essentially our group in Würzburg, my PhD student Tristan Harder, and Alex Dikopoltsev from the group of Muti Segev. All right, so I'm almost at the end of my time and of anything else. So where to go next? Of course, you can leave 3.5 semiconductors and you can go to organic materials as we've done here. So you have a single trap as well, but now you have a hemispheric cavity encapsulating your organic material. You can couple this and you can create lattices with that. And that's also something that I've showed you at the beginning. We're not the only ones doing that. So in doing so, you can create an SSH model as well. Here, a linear one, And when you do that, you can get this localized effects. And in order to see that I'm not too late for teaching and there is some time still for your questions, I'm going to speed up. The majority of my talk is done. There are some things I want to highlight that we're doing. So this is lasing from a topological laser using a fluorescent protein. We can go to two-dimensional lattices now, which is really technologically quite challenging because you have to sandwich this material between two mirrors. But here I show you some unpublished data that is a honeycomb lattice using at room temperature using this organic materials. And then there is well, we're also looking for topological lasing. There's a plethora of materials that not only us are interested in. So we are very interested now in new functional materials like organic emitters, fluorescent proteins, J-aggregate emitters. There's a lot going on TMDC materials, and of course on perovskite, our colleagues from Singapore working very successfully, also having a SSH model realized with a perovskite emitter, and this is also something that we are currently occupying ourselves with. And one thing I want to highlight when it comes to topology is, of course, this sandwich option, right? You have a bottom mirror and a top mirror is quite neat because you can in principle put anything you like. And one thing you can put, of course, is you can put TMDs and you can put specifically moire excitons where you twist one layer next to the other. So here I borrowed from this colleagues. So you have an engineered excitonic landscape, and then you can actually find proposals that that show theoretically topological excitonic bands in moire heterostructures. And this is, of course, something quite exciting where the topology is already in the excitonic band structures then that we can then couple to light field and investigate them. So this is something I'm quite excited about and I'm currently occupying myself with. A quick shout out to my own group, the people I worked with. This is my own group. This is some colleagues here in Würzburg that I worked with. I showed you a lot of data in close collaboration with Muti Segev from Technion and his brilliant student Alex Dikopoltsev. Of course, theoretical collaboration with Ulf Peschel, Oleg Egorov, Timothy Liu, Ivan Savienko, and a bunch of other colleagues that I cannot name all of them. I will leave this here and I thank you for your attention.
Thank you very much, Sebastian, for this really wonderful talk. Beautiful results and really a very broad spectrum of activity.
Thank you very much.
If you please, for the audience, if you raise your hands and I will take you in sequence. So we don't have so much time, so I will go straight ahead to Anton Zasedatelev. Anton, please unmute your microphone.
Hello, thanks, Sebastian, for the very nice talk. I have a question.
Hi, Anton. Of course.
I have a question to electro-optic effect.
Yes.
It was slide number 13, I think.
Yes.
It's actually a very interesting way to tune the system. I was actually wondering if you can make a kind of a grid on top of your pillars and address each of the pillar separately.
That's a very, very interesting question. And one thing that I can tell you that is not a secret we're working on is working with ITO and transparent contacts, which is not completely so indium tin oxide, which when done correctly has a good resistivity and is reasonably transparent. So that's something we work on right now in homogeneous layers, but we have thought about creating grid. Whether we get exactly the resolution that we would need for, let's say, 3 micron for 3 microns is not so sure. But one thing I give you an example, what I would be interested in is finding a way to locally create potential barriers when studying propagation in lattices. I'm thinking of stuff like Klein tunneling, which is a fundamental quantum effect in honeycomb lattices where you could create barriers with that. Whether you can really address individual pillars, we'll have to see.
Okay, because then maybe you can also solve the problem with the disorder in a weakly coupled system, such that you can.
That is true, but for now, I would say that using your spatial light modulator to do that is probably much easier. But yes, in principle, this would be a similar approach if you want. Yeah.
Yeah, thanks. And probably a very quick question. Can you comment a little bit on the difference in coherence for the trivial modes with respect to the topologically protected ones? Which one are more coherent, and yeah, how would you compare them?
You mean on the topological laser, the topological VIX
exactly,
that I've shown you? Yes. Well, what we'll actually say is that we have lasing from multiple modes. I have to click quite some slides, so I start speaking. In the trivial case, you actually have several different wavelengths, and you have this, what I would call patches. Yeah, pretty much like the ones you have here, but of course they are not red, green, and blue, but you have slightly different wavelengths, and they are not phase locked to one another. So you need to create this propagating mode that has to do some propagation around this interface. And from this propagation around the interface, you get actually injection locking. And here you don't have the effect where you have typically, when you think about that conceptually, you have one master device and you have a bunch of other devices, and you have one that imprints the phase onto the other one in injection locking. Here, this is not the case. You have the nth laser that locks to the n plus 1, plus 2, plus 3. So you have a closed circle, if you want, and you have propagation in the system. And it's actually quite interesting for us because studying non-linearities that couple dynamically is very, very difficult, because in theory, everything, all your calculations will diverge and explode very quickly. It's very challenging to even couple 2 or 3 or 4 strong non-linearities and then discuss not some final steady state, but dynamics and how they start to oscillate. So this is something we're looking at experimentally using street camera techniques and pump probe techniques, because we think it's quite exciting to understand how the system finds a state in which all of these lasers are coherent with one another.
Okay, thanks. Thanks again for a very nice talk.
You're welcome.
Thank you. Let's move on to Tamsin Cookson.
Hello, thank you for the talk. I was actually on this slide, I was wondering the ratio between the stretched and compressed cells and this other, the barrier, the yellow section that you have highlighted here.
Yes.
How dependent is your your topological gap has to be quite dependent on this. If you vary, like, what is the most important?
Yes. I can. It's a pity that I have not prepared that, because we have done an experiment. I can tell you about it. So it's very important, and you have 2 limits that I can quickly explain to you. You have this radial micropillars, and here they are etched. So what this means is you cannot separate them such that they have an air gap, because then they will not couple. So a coupling that we would call 1 would mean they would just touch. A coupling, we normalize the distance between them by the diameter. So 1 would be touching, smaller than 1 would be overlap. If you overlap more than 40%, at some point you lose any sense of tight binding. You don't have individual sides that couple, but you have some elliptical thing with new modes. So you are in between that. You're roughly in between 0.6, 0.7, so relatively strong overlap, and just touching, which I would call 1. And then you have to create 5 coupling parameters, distinct coupling parameters. So when we do our electron beam lithography, we have to be accurate to the second digit of that. And when you do that, you actually can achieve this quite similar and relatively large band gaps. So it's quite important. And now you're basically limited by the uppermost and lowermost one. But you can of course make the deviation smaller. And now you have to believe me, because I haven't included this here, but we have done this. And then your topological gap is of the order of the line width. And then what you will see here, I hope you can see my cursor, is that when you go away from the autocorrelation point, you find a curve like this, We actually had that when we submitted the paper. We thought we measured it later on after the first submission, but it was accepted so quickly, which is not a problem at all. But we didn't include this anymore. So we have a measurement that has a smaller topological gap, and that actually shows that the coherence decreases when you go away from the autocorrelation point. So it's absolutely crucial that you get this this coupling ratios right. Yeah.
Additionally, I wondered how this coherence changes when you go to the 200 Kelvin. I don't know if you showed this or if I.
Well, I did. It is more
sorry.
noisy. Very no. Well,
Yeah.
you don't have to be sorry. I did. I didn't show the line plot. It's not as perfect as before, but you still see that you have a high degree of coherence when you go along this. It's not fully one anymore, and this design wasn't intended to work at all. But we were still stunned to see that the whole concept holds, because you still have a topological mode within the gap. It is still narrower than the gap. You have, of course, much more noise, much more phonon scattering and other effects in the system. But in principle, this is very robust also to temperature changes. But nothing gets better when you go from 4K to well, not nothing, but in this case, it's not getting better, it's getting slightly worse. But we're still confident enough to show rather this idea of robustness. We discussed this a lot because we didn't want to say we're limited to 200 Kelvin, because this is simply a limitation of the active material in this case, not at all of the defect. So we discussed a lot internally, should we show this, or do we do something at room temperature and show temperature changes then? But we decided to do that. Yeah.
Thank you very much.
You're welcome.
Okay, so let's move on to Helgi Sigurdsson.
Hey, Sebastian. Thank you very much for a very nice talk.
Thank you.
So,
Thank you.
sorry, I don't have a camera on this computer, but I mean, you know how I look like. So
yeah. I hope you're good still. Yeah.
So my question is very simple. It's about the wavelength tunability of these topological lasers. So
Yes.
are they are they going to be compatible with other devices, or do we have a few nanometer tunability for these lasers to sort of play around with them?
That's a very interesting question, because that in the end will depend on the fact how this interface will actually look like. There are several techniques that allow you for wavelength tunability, and actually temperature can be one of them. And currently we think temperature is the one that will work best. That's of course not a fast way to do that. Because at the end, of course, we are at the stage now where we are looking for the question to answer the question, how many can we actually couple? And we want to, of course, increase our ratio of interface to bulk. So you cannot only do a hexagon, you can start folding this interface to have as much interface to bulk as possible. And then we have to see how we can homogeneously find an effect that homogeneously addresses the whole system such that we can have tunability. Temperature is certainly one of them, but we are also looking into other effects. But there's certainly a lot of unanswered technological questions with that, let alone if you think really into the direction of technological applications away from fundamental physics, then you need, of course, to see how you can pump this electrically.
Mm-hmm. All right, thank you very much.
You're welcome, Helgi.
Okay, next question from Paul Iskan from Trinity, Dublin.
Hi, thanks.
Hi.
And thanks, Sebastian. That was very nice. I wondered, in these topological edge modes, in this ring geometry, essentially, if you can say anything about the angular momentum of the mode that condenses, right? You know, do you know that it condenses with no vorticity around the ring, or one vortex, or 27 vortices, or something like that?
You talk about what I'm showing here on the left side.
Yes, I mean, yeah, you're.
I mean, yes, I've been showing this. Sorry.
Yeah, these kind of.
I'm guessing. So they implemented the Haldane model, and they implemented. Sorry, this is taking me a bit here. So this is what is called the Hafezi model, which is this interlink couplers that create this artificial gauge field. And you can also do the Haldane model, although it is so fragile that they I think that they have decided to go for this Hafezi model here. It's actually a very good question that I cannot answer straight away. I have to admit that I'm not really an expert on this system, whereas I can absolutely refer you to write an email to Moti Segev and to reformulate that question, because I think it's a good one, but I would have to think about that and get back to you.
No worries, thanks.
You're welcome.
Okay, so we have one more question from Stepan Barisev.
Hello, thank you very much for a great talk. A small, maybe technical question. On slide 36, I still cannot wrap my head around why you have a higher coherence for not in the autocorrelation points. There is some hotspots on the ring geometry, but on the autocorrelation points, it seems like the coherence is less. Can you explain that?
You're right. You're right in a sense. It's quite complicated. You're right that in principle you should have the highest coherence here. However, you're looking through the prism of how accurate you overlay one with the other, and then how good the fringe visibility actually is. Be very careful here. What you see here is not fringe intensity, but overall intensity. So what you see here basically is this corner was a bit brighter than this one, and this corner was a bit brighter than that one. And what it seems is that our accuracy in measuring these fringes has slightly depends on this as well. So we get some noise off from our experiment, because normally you would expect exactly what you say, that the autocorrelation point is really our points of highest spatial coherence. Here, this is, well, not exact. It's not that it's much below, but here you, for example, see that this point shows the highest fringe contrast of those. We do not think that there's much physical meaning behind that. So essentially our error bars here on this red data points are larger than the deviations. But what we can clearly say is that this part here, that is basically the furthest away from the counterpart, they are pretty much as coherent within the noise than the autocorrelation point, which is our reasoning why we say that this is really fully coherent, and it doesn't really distinguish between the autocorrelation points and all the other ones. But you're certainly right, there is some noise that we get from the experimental technique on this. This is not easy to measure. We did try to use a global phase, so do this in a Mach-10 interferometer with a blown up reference mode and all other ones. This is the one that was the most convincing way of showing this.
I see. Thank you very much.
You're welcome.
Okay, and with that, I would like to thank Sebastian again. And let him go on for his teaching, and everyone.
Yes, thank you very much. It's all right. They will wait for me.
Okay, Sebastian, thank you very much, and thanks to all the people who attended this seminar. So we will let you know about the next one. So have a very good day, everyone.
Thank you very much. Bye.
See you. Bye.